In this module, we're going to look under the hood to see how Bitcoin really works. You'll get a tangible understanding of exactly what's going on and what it takes to create applications that interact with Bitcoin or utilize some of the ideas behind Bitcoin. While this module will be more technical than the previous and have a small number of coding examples, my goal is to stay mostly at the concept level so non-developers can follow along also. That being said, the rest of this first clip and the second one will focus on the Bitcoin software landscape and the installation of a specific tool, Bitcore. This gets fairly detailed as there are a couple tricky aspects, and I want to make sure developers can quickly get up and going writing some basic Bitcoin code. Feel free to skip clip 2 if you don't have any plans to write code. The rest of this clip will give a broad overview of the Bitcoin software landscape. When Bitcoin first came out, there was only one piece of software that did everything. It contained the wallet functionality we talked about in the previous module, creating private keys and addresses, and creating and signing transactions. It also carried out bookkeeper tasks, checking transactions, recording transactions into the ledger, relaying those transactions, and voting to synchronize with other bookkeepers. Now you can use software that only provides the functionality you need. Most wallet software, or thin clients, only handle address and transaction creation, but do not check or relay transactions or maintain a full ledger. This makes sense as many wallets run on mobile phones or on computers where the owner does not want to dedicate the resources to maintain a full ledger. Programs that check every transaction and maintain a ledger are called full nodes. I want to emphasize that this really does mean the program receives and records every transaction produced in the entire world. The current ledger, including all historical transactions as of January 2016, is about 50 gigabytes and can use over 100 gigabytes depending on how your software stores and uses it. Bandwidth requirements can exceed several hundred gigabytes per month to share that ledger with other nodes. The benefit is improved security by verifying every transaction yourself, and also better privacy since your node relays many other transactions beyond just your own. Full nodes also have wallet functionality. Bitcoin Core is the official full node and is available at bitcoin.org. The voting or mining functionality has also been partitioned off from full nodes since, as mentioned previously, to be competitive, this requires specialized hardware. The software in these groupings can all be considered clients that interact with the Bitcoin network. There are also many libraries that don't necessarily connect to the network and just provide tools to create and interpret Bitcoin data. Both tools and clients are available in just about every popular language, including Python, Java, Ruby, Go, and more. I'll be installing Bitcore, a JavaScript-based open-source package of tools made by BitPay. I'm using it because JavaScript is a fairly well-known language, and also because it utilizes the core C++ Bitcoin code underneath, so there's less risk of differences between Bitcore results and the main Bitcoin code. This clip will provide a detailed walkthrough of getting the Bitcore library installed and using it to create a Bitcoin address. You'll want to go to bitcore.io to get the latest instructions, as they may have changed since this course was released. There are a few requirements we need to install prior to Bitcore, but I'll walk through step by step. Bitcore runs on Node.js, a JavaScript runtime environment, so we need to install that first. Furthermore, we need a specific version of Node, 4.2, which I prefer to install using NVM, or Node Version Manager, a program that makes it easier to maintain multiple versions of Node on one machine. NVM only runs on Mac and Linux, but the GitHub page mentions some alternatives for Windows. It also requires a C++ compiler, which you can get on a Mac by installing Xcode. Keep in mind you can also just install the correct version of Node.js directly without using NVM. NVM installation instructions can be found at github.com/creationix/NVM. I'll be installing version 0.30.2 on a Mac running El Capitan 10.11.2 and Xcode version 7.2. I simply copy in the install script, which downloads and compiles NVM. Once NVM is installed, I close and reopen my terminal so my bash profile reloads and activates NVM. Then we install version 4.2 of Node by typing nvm install v4.2. Confirm the right version is available by typing node-version. If you see something other than 4.2, you may already have installed Node.js and may need to uninstall it. Also, if the node command is not found, you may need to type nvm use 4.2 to load the correct version of Node. This is sometimes needed when you restart the terminal. Now we will install Bitcore. We use npm, the package manager that ships with Node.js. npm makes it easy to publish your own code for others to use, download software packages, and get updates on those packages. npm install-g Bitcore. That -g installs Bitcore globally, which means the Bitcore library can be used by any node project you set up. We see it here in my nvm directory. Without the -g, it would install in your current directory. Let's make a new project. First, make a directory, then go into that directory. Now run npm init to initialize a new project. Just hit enter to use the defaults. You can change any of these in the package.json file the init command generates later if you'd like to publish your project. The package.json file is a file that describes the project and lists its dependencies. If you open a text editor, I'm going to use Atom. You can see the default state, which has things like the name and version. Now we're going to include the Bitcore library as a dependency. npm install bitcore lib --save. That command creates a node modules directory with bitcore lib inside it. That --save command updates the package.json file to include bitcore-lib under dependencies. Note my package.json has a new line under dependencies. The advantage of keeping your package.json file updated with dependencies is that you can copy that single file, package.json, to a new project, type npm install, and it will automatically install any libraries you listed in that file. With all those prerequisites, we're finally ready to write some code. We're going to create a Bitcoin address. Type node to enter the interactive shell. We load in the Bitcore library first with the require function. Now let's create a random 32-byte number. That returns a string of bytes, and we can convert it to a number format with bitcore.crypto.bn. If I type rand number by itself, we see the hex version of this number, and if I type toString, we see the decimal version. Let's make a Bitcoin address from this. First, use the private key command, and then toAddress, and then type address to print it out. You could copy and paste that address into any wallet program and send money to that right now, but don't do that. If you close the terminal window and lost the private key, any funds sent to that address would be gone forever. From now on, I'll use what's called the testnet, a fully operational Bitcoin network to test code on where you won't risk losing any real money. I do this by specifying testnet in the toAddress function. You can see the address looks different now, and real wallets won't let you send funds to it. Compare the process of generating a Bitcoin address to signing up for an email address at Gmail, for instance. On Gmail, I have to check with Google to see if an address I want, like scott@gmail.com, is available. On Bitcoin, I just picked a random number and ran some commands that transform it into an address. I didn't check any central service or even the Bitcoin network to see if that address was already in use. How is this possible? What if I picked an address someone else was already using? Before I elaborate on this, let me explain just what Bitcoin addresses are and how they work. As mentioned in the first module, when Bob sends money to Alice, he authorizes that transaction with a digital signature, the digital equivalent of a handwritten signature that is much more secure on the internet. Digital signatures are an integral piece of Bitcoin addresses. Let me take a few minutes to explain digital signatures. Digital signatures are based on public key cryptography. When I hear cryptography, I think about encrypting secret messages. For instance, I might want to send a secret message, "The enemy is attacking," and apply a trivial encryption scheme to avoid anyone reading the message. I could create a table that replaces each letter with a different letter. My recipient could decode my message with this same table or key. Instead of one key that both encrypts and decrypts a message, public key cryptography uses a pair of keys where each one only works in one direction: a public key to encrypt a message and a private key to decrypt it. My recipient can publicly post her public key, which then I use to encrypt my message. Then she decrypts it with her private key. The advantage is that I can send her a secret message without ever having to meet to share a key. The math behind this technique is based on one-way or trapdoor functions, things that are easy to calculate one way but not the reverse. For example, it's easy to multiply 199 and 337 together, but it's much harder to find the factors of this number. I have to try a bunch of numbers. Does it divide by 3? No. By 5? No. By 7? Etc. The algorithm in Bitcoin is based on finding a discrete logarithm on an elliptic curve rather than factoring numbers. Without going into the details of this, the primary benefit is a smaller key size for a given amount of security. So what does this have to do with digital signatures? If I relabel this drawing, this same algorithm can be used to prove ownership. Instead of starting up here, I begin with the message in the middle and use the private key to generate a signature instead of decryption. Others can then use the public key to get back to the original message. If the message generated by the public key and signature matches the original message, we have proof the signature was created by Bob's private key. We also have proof that the message hasn't been altered because the signature is in part based on the message. So the same operations used to encrypt a message provide a mechanism for proving the authorization and integrity of a transaction. Getting back to Bitcoin addresses. Each address is basically the public key from this digital signature algorithm. When Bob sends money to Alice, he's assigning funds to that public key. Alice then spends those funds by generating a signature that proves she's the owner of that public key. You can think of a Bitcoin address as a public Dropbox where funds can be deposited by anyone, but only retrieved by the owner of the private key for that box. If we look back at the code to create an address, we see that the first step is to generate a private key, which is basically just a large random number. The elliptic curve math then provides a way to calculate the public key from this private key. There's no way to go back from a public key to a private key. If that were possible, you could steal any coins you wanted. Interestingly, Bitcoin addresses started out just as public keys, but now they have a few more operations to help prevent errors and enhance security and privacy. More on this later. Let's return to the question I asked earlier. If creating a Bitcoin address is just picking a random number, how do you avoid picking a random number someone else has already used, and what would happen if you did pick it? Since that original random number is the private key, you would be able to spend any funds sent to that address. But this is incredibly unlikely because there are so many possible addresses. If this seems hard to believe, it should be. There's nothing in our daily lives that is remotely comparable. There are about 10 to the 24th atoms in a cup of water, which is by itself an unfathomably large number. You can generate trillions of addresses a second for 1,000 years and still be short of the number of atoms in that cup of water. But the number of possible Bitcoin addresses is much, much larger than the number of atoms in a cup of water. It's closer to the number of atoms in the entire Earth. This large number underlies the security and privacy behind Bitcoin addresses. Funds are protected by the extraordinarily low possibility of guessing someone else's private key. Also, this way of generating addresses does not require any contact with a central registry or even the Bitcoin network itself. I can generate an address by flipping a coin 256 times without ever telling anyone. Now that we have an understanding of addresses and how transactions are authorized, let's dive a little deeper into those transactions and how they're stored in the decentralized ledger. One surprising aspect of Bitcoin that I've oversimplified so far is that no balances are stored. The main ledger only stores transactions. But without balances, how do you find out how much money you have? And if Bob creates a transaction sending 5 Bitcoins, how do you know he actually has 5 Bitcoins to spend? To spend 5 Bitcoins, Bob's transaction must source one or more previous transactions that have sent him 5 Bitcoins. And those transactions must in turn source other transactions all the way back to special coin-based transactions that have no inputs where money is effectively created. More on these later. In this way, transactions form an ownership chain. To calculate how much money you have, you need to iterate through every transaction with one of your addresses and add where you've received money and subtract where you've sent money. While this may seem cumbersome, applications maintain an index that makes this fast. There is also a simplifying rule that every input must be spent completely in a transaction. This way, applications only need to keep track of unspent transactions and not partially spent ones. Let's look at a real transaction at blockexplorer.com to see how this works in detail. This transaction is sending 0.2495 Bitcoins, which we can see in the output list. The transaction references 3 input transactions. Now, because those input transactions don't add up to 0.2495 exactly, and because of the rule that each input must be spent completely, a second output, or change output, returns the extra to another address, most likely also owned by the sender. We don't strictly know which is the real amount the sender wanted to send versus the change, but it's likely that the bigger amount is what the sender typed into his or her wallet, since the smaller amount wouldn't have required as many inputs. These outputs can then later be used as inputs for other transactions. The software that bookkeepers run keeps track of these so-called unspent transaction outputs, or UTXOs, in a separate database because this database needs to be checked often. Anytime a new transaction comes in, its inputs must be checked against this database to ensure it's valid and not trying to respend an output. Overall, this structure has some privacy implications. It's best practice in Bitcoin to generate a new address for every transaction, including the change address. This makes it harder to connect transactions together to learn about someone's total balance or buying behavior. But as we see with this transaction, addresses are often linked together when you want to spend more than any one transaction output can supply. In order for Bob to spend 5 Bitcoins, he must source a 2 and 4 input transaction to cover that, since each one by itself is insufficient. If I go back to the real transaction and expand the details of the inputs, you can see something called a script SIG under each input. Part of this is the digital signature created by the owner of the address for each input. The signatures prove authorization, but here they also prove a connection between these addresses, as the sender must have had the private keys for all these addresses. If a real identity can be linked to one transaction, it's possible to trace through this ownership chain and statistically connect other transactions to it. This is why Bitcoin is not anonymous, but pseudonymous. If, for example, I buy Windows from Microsoft, which, by the way, now accepts Bitcoin, now Microsoft knows an address I own and could potentially connect other transactions I make to that one. If we look at the output details of the transaction, we see something called a script pub key. You may have wondered why the signature was labeled script SIG before. The inputs and outputs are actually more flexible than a simple from and to address. Bitcoin uses a scripting language to open up the possibility for more complex transactions, such as requiring 2 out of 3 signatures or even storing data. You can think of each output like a puzzle that needs to be solved to be spent. To summarize Bitcoin's ledger so far, we see it's a giant collection of transactions. Current balances are the sum of all the unspent outputs of those transactions. And to spend those, you reference them as inputs to a new transaction and provide the script that unlocks each one. One question many have had is why Bitcoin uses transaction inputs and outputs to track ownership rather than a more familiar ledger of accounts and balances. I believe one of the primary reasons was to enhance privacy by avoiding multiple transactions linked to a single account. But as we just saw, Bitcoin transactions are still often linkable. There are several other pros and cons as well, for example, dealing with the storage space needed to keep track of accounts versus outputs. But considering that there are many systems that do in fact manage accounts and balances directly, like Ethereum and Ripple, I think the best answer I can offer is that there are many trade-offs, and no agreement that one way is universally better than the other. To solidify this transaction system, let's create one by hand using Bitcore and send it out. This is another clip you may want to skip if you're not interested in coding. The first step to playing with Bitcoin is to get your hands on some. We're going to obtain coins on the testnet to avoid losing any real money. If you Google Bitcoin testnet faucet, you can find several websites that will send you a small amount of test coins. I'm going to go to bitcointestnetfaucet.com. Now we need an address to send these coins to, so we're going to make a new address. However, it's important that we don't lose the private key to this address, so we're going to store that key in a file this time. Run node again and require the Bitcore library as before. Then generate a new random private key and add the following function at the end, toWIF. WIF stands for Wallet Import Format and is a format with some error checking and extra information to tell wallets what kind of key it is. Now create an index.js file where we'll both create and send the transaction. I'm first going to copy in that private key string from the console, then convert it to a private key, and then to an address. Save the file and go back to the console. If you're still in the node shell, exit by typing Ctrl-C twice. Then type node index.js to run the file. In the output, we see the address. Copy that and paste it into the faucet form. You need to get enough to at least cover the fee on sending a transaction. The minimum fees change according to market conditions, but BlockCipher has a page that estimates these for you. At this time, the fee is about 0.0005 bitcoins, so we'll type in 10 times that, or 0.005 bitcoins. Note that some forms are in Satoshis, which are the smallest unit of Bitcoin, 1/100 millionth, so you might need to convert these numbers on another faucet. Congratulations, you just got your first testnet Bitcoins. Let's see how to send those now. Go back to the index.js file and add the following lines to generate a second address to receive the coins. Here we're making a new address, but this time from a string instead of a random number. The string gets converted to a 256-bit number through a SHA-256 hash, which I'll talk about more soon. This is a very risky way to generate an address, as humans are bad at generating truly random input, but I wanted to demonstrate it. So now we have a from address and one output address. We need one more piece of information to be able to create a transaction, the input transaction. A given address may have several unspent outputs available if multiple transactions have been created sending money to it. We need to specify which one of those unspent transaction outputs are going to be our inputs. This requires a connection to the Bitcoin network. Go back to your console and now install bitcore-explorers. Now go back to our index.js file and add the following text. This function queries a server run by BitPay's Insight server, in this case test-insight.bitpay.com. The real power behind the Bitcore software is running your own full node and querying that instead of a server you don't control. You can do that by typing bitcore-d, but this currently requires over 100 gigabytes and several days of processing to set up. Running a full node means downloading and checking every transaction ever created and continuing to receive and relay all new transactions. It's an intensive task, but remember, this is the price of decentralization and minimizing trust. Every peer on the network maintains its own ledger. So for the sake of a quick demo, we'll just rely on BitPay's server, which the Explorer's library defaults to. I'm going to comment out the previous console logs before running the file again with node index.js. In the results, we see our address, amount, and a transaction ID with an index. Remember, transactions can have multiple inputs and outputs, so you need to specify an index along with the transaction. Okay, let's use that unspent output in a transaction now. First, create a transaction and then set the unspent transaction output as the from source. Then set our second address as the to address. And let's send the exact amount that's available in the unspent output, 500,000 satoshis. Now to send this transaction, we need to serialize it and then broadcast it using the Explorer's module again. I'm going to leave the broadcast function commented out for now. Now we got an error, something about the fee being too small. This is one part of transactions that I haven't discussed in depth yet. The Bitcore library provides some safety checks on transactions, and checking for an appropriate fee is one of those. Transaction fees are collected by the bookkeepers or miners, and if you don't have a sufficient fee, it's likely your transaction will get ignored. Interestingly, there's no fee field in a transaction. Rather, the fee is just the difference between all the inputs and outputs. To add a fee, we need to reduce the output to include one of the minimum fees we saw on the block cipher site, 50,000. I'm going to change my output down to 10,000 or 0.0001 bitcoins. Remember, all inputs must be spent completely, so we need to include a change address in order to send a small output with this larger input. Let's return the extra back to our original address. Note that best privacy practice is to generate a new address for the change. Now if I print out the transaction using tx.toObject, we can see that 10,000 goes to my destination address and 480,000 is going back to my change address, leaving a fee of 10,000. Bitcore automatically applies a default fee, but I'm going to increase it with the fee command just to be on the safe side. Now when we try to run the code, we get a different error, this time about inputs not being signed. This is where we unlock the funds. We need to use the private key associated with the address in the input transaction. If I print the transaction out again after signing it, we see a script applied to the inputs. I mentioned before that these are more than just digital signatures, but rather a small scripting language. If I print out both the input and outputs with the script2string command, you can see some of the commands in this scripting language. It turns out that the default output is more than a public key, but a function that says something along the lines of provide a signature and public key such that the hash of the public key matches the Bitcoin address, and the signature, transaction, and public key all verify together. I'll explain hashes shortly, but for now just think of them as a compression function. When I first introduced Bitcoin addresses, I noted that the address is not just a public key. It's actually a hash of a public key with some extra conversion to avoid easily mistaken numbers and letters like zeros and O's. This is why the script has some hash commands in there. Another type of much more flexible output puzzle is a pay-to-script hash. To unlock this output, you must supply a script that hashes to the value supplied. This is commonly used to enable outputs that can be unlocked with 2 of 3 private keys. A final output worth mentioning is the data store, implemented with an op-return command. This output can never be spent, but can be used to permanently store a small amount of data in the ledger. If, say, you invented a new product, you could store a hash of a description of that product in the ledger to have timestamp proof of when you invented it. Bitcore provides a function for this, tx.addData. Note that this still costs a fee and is also a dead-end output. Any money sent to this address will be unspendable. With those details explained, we're finally ready to send the transaction using insight.broadcast. If it works, you should see the transaction ID returned. We can now go to a block explorer for the testnet and type in either the address we sent the money to or the transaction ID just returned. Congratulations, you just wrote code that successfully sent a Bitcoin transaction. Now remember, we used a BitPay server to broadcast this transaction. We could have also run a full node ourselves to talk to other Bitcoin peers of our choosing and directly broadcast the transaction. Several sites also provide web forms that accept raw transactions and broadcast them for you. This is useful if you don't have a full node running and are using another library that can't directly broadcast a transaction. To do this, I print out the raw transaction and paste it into the raw transaction form, which here is at test-insight.bitpay.com. The Bitcoin addresses, digital signatures, and transactions we've seen so far provide much of the security behind Bitcoin. Without a private key corresponding to a given Bitcoin address, it's impossible to forge a transaction to steal money from someone else. So, while we have a secure system for transferring tokens of value, we haven't talked about how those tokens are created in the first place, and that is the crucial other half to the security behind Bitcoin. We saw a brief mention of coin creation already, so-called coin-based transactions that source no inputs. But these transactions are permitted only under very constrained circumstances. If anyone was able to create Bitcoins at will, Bitcoins would no longer be scarce and the whole system would collapse. Preventing the invalid creation of coins is more subtle of a challenge than just the regulation of coin-based transactions. Consider that Bitcoins are nothing more than digital information and how easy it is to make copies of digital information on the internet. An MP3 music file can be duplicated with a simple download. What is it about Bitcoin that enables it to remain uncopyable and scarce? Allow me to describe a problematic scenario. Suppose I make a copy of the Bitcoin ledger, spend all my money, and then show a merchant the original copy of the ledger I made and say, look, the ledger shows I still have money. I'll create a transaction giving you the money in my balance and you give me that TV. It's crucial that the merchant can tell the difference between the fraudulent ledger I show him and the real one in which I have already spent my money. If he can be tricked into believing my ledger, I can effectively double spend my money or, put differently, create new money. Expanding on this, what if a rogue group of bookkeepers decided to try and trick a merchant? Given a choice between several ledgers, the best we can hope for is to follow the ledger the majority of bookkeepers support. And this brings us back to the voting system discussed in the first module. The voting system enables anyone to see which ledger the majority support. It also enables the bookkeepers to decide on a ledger version. Now, why would bookkeepers ever disagree about anything? Why are decisions even necessary? The bookkeepers need to reach consensus on fundamental aspects like when and how money is created, but also more mundane issues like regular software feature upgrades and fixes. The decentralized nature of the network also necessitates decisions about transaction order. Recall the double spend scenario from the first module, where Bob sends both Alice and Carol all his Bitcoins. On a more detailed level, he could create two transactions that both source the same unspent output from a previous transaction. These transactions might reach different bookkeepers in different orders due to network delays, or Bob even intentionally sharing them in different orders. Bookkeepers that receive the transaction to Alice first would ignore Carol's because it would be trying to spend an already spent output. Bookkeepers receiving Carol's first would ignore Alice's. And so we see that, in addition to deciding on system rules, deciding on transaction order is crucial because that order changes who has money. Let's now dive into this voting system. I mentioned in the first module that bookkeepers must solve computational puzzles to vote. This gives voting a cost, making it financially infeasible for a single anonymous voter to masquerade as many others and sway the vote. It also provides a form of proof to the rest of the world of the majority's will, because the solutions could not be generated without the majority's computing resources. Let's see how this works in detail. The math puzzle being solved involves a cryptographic hash. I'm going to spend a few minutes explaining this because it's such an important component of Bitcoin. A hash function is a function that compresses an input into a kind of fingerprint. For example, I'm going to hash the word cat with a simple hash function. I'm going to assign each letter a number for its place in the alphabet, add them together, divide by 5, and then use the remainder as the result. So cat becomes 3, 1, 20, summed together is 24, divided by 5 is 4 with a remainder of 4, so 4 is my output. Dog can be hashed similarly. 4 plus 15 plus 7 equals 26. 26 divided by 5 is 5 with a remainder of 1. In this way, any word or sentence can be compressed into the numbers 0, 1, 2, 3, or 4, the possible remainders when I divide a number by 5. Note that the process is deterministic, that is, a given input always results in the same output. There's no uncertainty or randomness. Hashes are commonly used as a way to look up things faster. Imagine a phone book where instead of arranging names in alphabetical order, we use a hash function to decide what page to write each name in. Then to look up a name, we run the hash and go to that page to find the name. This method could be faster than an alphabetical sorting for names like Smith that cover many pages. A good hash function won't give the same answer for many inputs. Our phone book example wouldn't be good if half the names in a city mapped to the same page. A cryptographic hash function also has the goal of irreversibility. That is, given an output, it's extremely difficult to guess what input generated it. My simple hash function is terrible for this. It's easy to find a word such as oranges that also maps to 4, the same as cat. The cryptographic hash used in Bitcoin is called SHA-256, maps inputs to a 256-bit number, and is much more sophisticated. Here are the results of cat, dog, oranges, and orange singular. Note how orange and oranges are completely different. It's impossible to deduce anything from the input based on the output. Now, SHA-256 is much more complicated than my hash function, but a simple way to think about it is as a mixer. Part of what happens includes rearranging, combining, and remixing over and over again. There's a great walkthrough of this at metamorphosite.com if you'd like to see exactly how this works in detail. The irreversibility makes it useful for checking the integrity of files. By checking the cryptographic hash of a file, you can be sure the file is authentic down to every bit. It's impossible for someone to create another file with that same hash. Going back to Bitcoin, the puzzle being solved by the bookkeepers is the very thing I just said the cryptographic hash was designed to make difficult: finding an input for a given output. Specifically, the goal is to find an input that results in a hash output smaller than a certain target. The smaller the target, the fewer the number of outputs that fulfill that equation, and the harder it is to find a successful input. Let's connect this back to deciding on transaction order. As new transactions are created, they are forwarded around the network but not considered accepted into the official record yet, and are instead placed into a pool of unconfirmed transactions. Bookkeepers draw from this pool to create a candidate next set of transactions to be officially accepted, called a block. The full text of all those transactions is then input into the hash function, along with a previous block's hash and a random number called a nonce. Bookkeepers try different nonces until the resulting hash is below a target number. Because this is a cryptographic hash, there's no way to find an input that works other than by trying different guesses. It's statistically just like rolling dice until you get, say, 2 sixes in a row, only much, much harder. As of January 2016, the bookkeepers are trying over 1 quintillion or 1 billion hashes per second. At this point, all bookkeepers are in a competition to solve the hash first, each working on a potentially different set of transactions. When one bookkeeper succeeds, she announces her solution to the rest of the network. While transactions may have reached bookkeepers in different orders, one single bookkeeper chooses the next set of transactions. The hash function makes the decision maker a random one. Everyone then checks that block and the transactions in it, and begins working on the next block. Note that while solving the hash puzzle requires many billions of guesses, verifying the solution is trivial and just requires one. Because each block contains the hash solution of the previous block, the blocks form a chain, placing transactions in order. Occasionally, 2 bookkeepers will solve a block at about the same time, creating a fork in the blockchain. A fork might also occur if some bookkeepers decide to switch to a different set of rules that others don't accept. At this point, bookkeepers need to decide which branch to build on. That is, which block hash should they include in the input to the hash function along with the next batch of transactions. Which branch to build on is the voting choice the bookkeepers make. Now, in normal circumstances, forks quickly resolve. I mentioned that finding a block solution is like trying to roll 2 sixes in a row. Sometimes you'll get lucky and get 2 sixes on the very first 2 rolls, and sometimes you'll get unlucky, needing to roll the die hundreds of times. This statistical spread in how long it takes to solve a block means that it's very unlikely for 2 blocks to be solved at the same time, and even more unlikely for additional blocks to be solved at the same time. In other words, one of the branches will grow before the other very soon. The general rule is to always accept the longest branch available as the authoritative branch. The difficulty target is adjusted periodically so that the average block solution takes about 10 minutes to find. As more and faster computers have joined the network, the difficulty has increased substantially. Strictly speaking, since blocks have changing difficulty, the authoritative branch is not the chain with the highest number of blocks, but the chain with the most cumulative difficulty and work. So why 10 minutes? There's no reason for the exact number 10, but there's a balance between accepting transactions quickly and creating instability and waste in the network. During the time a recently found block is being distributed, other bookkeepers will still be working on a now stale branch, wasting energy. The shorter the block time, the higher the percentage of the total block time will be wasted and the greater the chance for forks. The fact that the end of the chain can fork and be rearranged means that transactions toward the end of the chain shouldn't be trusted as much as ones further back. Each block that gets added onto a transactions block is said to add to that transaction's number of confirmations. 6 confirmations means 6 blocks back and is the recommended number of confirmations to wait for high-value transactions. Note that transactions in the discarded blocks are not gone forever, they simply get placed back into the unconfirmed transactions pool and are included in subsequent blocks. I began this section stating that digital signatures alone only safeguard the transfer of bitcoins, not the creation of them, which must be carefully controlled to keep bitcoins scarce and valuable. I can now explain when and how bitcoins are created. The bookkeeper who solves a block gets a block reward and is allowed to include a Coinbase transaction, that is, one with no inputs, in the block he solves. This effectively creates money out of thin air. Currently, the transaction value is set at 25 bitcoins, but this cuts in half every 4 years until no more bitcoins are produced. As I mentioned in the first module, this discovery of money is why bookkeepers are called miners, but again, their real job is to maintain the ledger. The random nature of the block hashing puzzle simply provides a way to randomly distribute money into the world over time. In addition to the block reward, the bookkeeper who solves a block also gets the fees attached to all the transactions in that block. Here we see why it's valuable to include a decent fee in a transaction. If a transaction has no fee or a lower fee, bookkeepers may choose to ignore it or at least deprioritize it over other transactions. Finding a solution to a block and getting the block reward is extraordinarily hard. It's very much like winning the lottery. In Bitcoin, your chances of winning are based on what percentage of hashing power you have relative to the rest of the network. To increase their payout frequency, most people join mining pools, which work collectively to solve blocks, and then pay out divisions of the block reward depending on how much work each participant contributed. The payout is lower, but much steadier. This brings me to another form of double spend attack. While mining pools enable bookkeepers to receive a steadier payout, they also centralize power to the pool operators. Currently, several pools have over 10% of the total network hashing power, which you can see at blockchain.info/pools. With so much hashing power, it's possible to change the blockchain. Suppose Bob spends a large amount of money for a rare painting, and that the seller delivers that painting after 3 confirmations. Now, if Bob can present a new longer chain in which that original transaction's output goes back to Bob instead of the seller, the bookkeeper network will switch to that chain and consider the original transaction invalid. To pull off the attack, Bob needs to build blocks faster than the entire rest of the network while he waits on the painting. While unlikely, someone that controls only 10% of hashing power could get lucky. Note that it's unlikely a mining pool would sabotage their own source of revenue, that is, the Bitcoin network. This example should help explain why transactions further back in the chain are more secure. Because each block builds on the hash of the previous block, any changes to transactions in a past block invalidate all the more recent blocks. For someone to change a transaction in the past and have that accepted, he would need to resolve all the subsequent blocks to catch up to the main chain. Some people have criticized Bitcoin for wasting electricity to solve these hash functions instead of something more useful. However, this function is exceptionally special. Just like trying to get several 6s in a row with a die, there is a well-defined relationship between work and solutions. It's this relationship that allows anyone to compare 2 different blockchains and have assurance that the one with the most solutions is the one with the most work done and therefore the one the majority of the world supports. The hash function also provides an unlimited supply of new problems that can't be solved ahead of time, since, as just explained, each block's solution is utilized in the very next one. A final topic to mention is SPV wallets, or Simplified Payment Verification Wallets. While a full node has a complete list of every transaction ever made that it can check against to make sure a new transaction is not already spent, mobile phone wallets don't have the resources for this. Mobile wallets must check with the full node to see if a transaction is valid, and ideally several full nodes. To do this, SPV wallets send a transaction hash to a full node, and the full node returns the block the transaction is in, along with the block headers for every block after that one. In this way, the SPV wallet can verify how many confirmations a transaction has. To avoid sending every transaction in a block, nodes send a much smaller amount using a Merkle tree. A Merkle tree divides up every transaction in a block into pairs and then creates a hash of those transactions. Those hashes are then paired and hashed all the way up to a single root. To verify that a transaction is in a block, the full node only needs to send enough hashes so that you can obtain the Merkle root from that transaction. To verify 938, I would need 434, 321, and 906, and then calculate 121, 543, and 432, the root. To aid privacy, SPV wallets don't ask about specific transactions, but rather a pattern that matches several transactions called a Bloom filter. In this way, full nodes don't know exactly what transaction a given wallet is interested in and send back several. This pattern can be made more or less precise. A broad filter provides more privacy, but comes at the cost of bandwidth for more transactions. In summary, the core of Bitcoin is an ordered list of transactions called the blockchain. Each transaction authorizes transfer of value from a previous transaction's output to a new output. Usually, these outputs transfer funds to a new Bitcoin address, but the scripting language allows for many more options, such as outputs that require 2 of 3 signatures or even storing data. Bitcoin addresses are essentially the public keys from public key cryptography, the cryptographic technology that ensures only the owner of a corresponding private key can authorize a transaction. Those private keys are formed independent of any central registry by picking a random number from an unfathomably large pool. While digital signatures prevent unauthorized transactions, they don't prevent someone from presenting a fraudulent ledger. The proof-of-work voting system not only allows bookkeepers to reach consensus about transaction order and system rules, but also prove to the world which ledger the majority of them support. Users can look at the solutions to the cryptographic hashes for a block and have assurance that the majority of the bookkeeper's computing power was needed to create them. If you'd like to go a level deeper to understand the specific formatting of addresses, byte-level protocol formatting, and exact rules, I highly recommend Andreas Antonopoulos' book, Mastering Bitcoin. Much of this information is now also available at bitcoin.org under the Developer section. Note, however, that the final say on the exact specifications can only be determined by looking at the source code running on the majority of miner or bookkeeper nodes.